Brought to you by Chemistry.
Traído a ti por la química.
Hello and welcome to Brought to you by Chemistry. What's brought to you by Chemistry? I might hear you ask. I don't, because, you know, the way this podcast works, we've recorded it beforehand. Brought to you by Chemistry? Difficult reactions? Yes. Difficult exams? Yes. Even more difficult romances? All of those things are true. But in this case, it is also a new podcast series from the Royal Society of Chemistry. Now, we have made it to the end. This is the final episode. Look, I've had fun. You've had fun. I've had even more fun. Now, what we're interested in here now we've got to the end, is we want to look at the future. In this episode, we want to see what the future could look like. What do you think the future could look like? That's a really great answer. I can't hear it. What exciting innovations are on the horizon, and how can these be incorporated into like a circular economy, into the future of our plastic? I don't know, and you don't know. And I know who does know. Who knows is our experts. In a first, both of our guests have a chemistry background, so this is double the chemistry fun for all of you nerds. Both of our experts are working on new sustainable technologies to help tackle the plastics crisis. So, expert, could you please introduce yourself? Expert one, I'm going to say Charlotte. Introduce yourself.
Thanks, Alex. Nice to meet you. And my name's Charlotte Williams. I'm a professor of chemistry here at Oxford University. And my research interests lie in how to make plastics from unconventional raw materials, for example, wastes like carbon dioxide or biomass. And secondly, how to improve the properties of plastics through using these different raw materials. And thirdly, how to design them from the beginning so that at the end, they don't cause the problems they currently do, so that you can recycle or degrade them when you're finished with them.
Wonderful. Expert two, can you please introduce yourself?
Hi, Alex. My name is Jo Sadler. I'm a research fellow at the University of Edinburgh in the School of Biological Sciences. Even though I was originally a chemist, I've slightly moved over. And so my research is all focused, sort of complementary to Charlotte's, really, on how to use biotechnology and a blend of chemistry and biotechnology to both degrade and then upcycle post-consumer plastics. So really tackling the giant mound of plastic waste that we've already created, and then in the future looking more towards, as you say, like designing for upcycling and life.
Fantastic. And what's really great about that is because you said that your work is sort of complementary. So with that in mind, I'm going to ask both of you, this first question is, what do you want the future of plastics to look like? That is a super broad question, so interpret it as you might like, and we can go from there.
Well, this is a very difficult first question, Alex. And I guess that we're going to spend the next hour covering some of my thoughts on this problem. But I would like to start with a connection that isn't always made about plastics. And that's the fact that the production, use, and disposal of plastics is absolutely interlinked with carbon cycles, and in particular with greenhouse gas emissions. And it faces a unique problem as a sector in decarbonizing, because at the minute it relies almost entirely on the same fossil fuels as we will use in liquid transportation. And because of this, decarbonizing this sector or reaching net zero is going to require a move away from petrochemicals. And I think that this is a part of the plastics problem that people haven't yet fully grasped. So we all understand the mounds of waste plastic that Jo referred to just now. We all understand well that there is a really severe environmental pollution, particularly from microplastics across a range of the environments, not just oceans, also airs and soils on Earth. But what we haven't quite grasped is how integrated this whole production of the material is also with carbon dioxide emissions. And we need to get to grips with that in order to properly solve some of the problems.
Jo, what do you want the future of plastics to look like? And don't say the exact same thing as Charlotte, because otherwise this will be a very strange, esoteric podcast episode.
Well, no, I think that's a really good point. But I also think, to me, one of the main messages I like to try and get across from my work, and to try and promote this message really that plastics, we think about them all wrong at the moment. I think people think of them as a kind of disposable, in many cases, a disposable product which is very low value. And I think we need to rethink the way that we think about these things and actually start treating the plastic and the material as a resource and start respecting its life cycle. So we really need the future needs to think about all stages, right from designing, for carbon neutral design from renewable resources, but actually then all the way through to the end of life. So we have technologies in place to efficiently break down these polymers into something that we can then turn into something else that's useful, rather than just thinking, oh, we've used this plastic as a waste product, let's throw it away. So we need to start, respecting these resources, respecting that they came, in many cases, they are still coming from fossil fuels, although that might change, and start to think about these as resources rather than a waste product.
So both of you have made super interesting points here. And I think our first episode looked at this question like entirely as a topic. So we're going to bookend it by asking you this question. Like, would you like to see the use of plastics eradicated entirely?
No, I don't think we should eradicate plastics. I think plastics are a very, very useful material, and they're used extensively in packaging, and this is a good thing because they are improving the shelf life of food, so reducing food waste, reducing transport costs and emissions. There's a reason they've been such a successful material, and I think we shouldn't deny the fact that they are extremely important across so many aspects of our lives. But what we haven't got right yet is thinking about these materials holistically and how they're going to fit into a sustainable future. And that's what we need to do now. And that's what we're really waking up to now. And I think if we can marry that with the fact that they are really useful materials, then we should absolutely have them in our future. We just need to design them properly and reuse them and treat them properly.
One of the things, Alex, so that I think everything Jo said is right. And one of the things that's a bit of a misconception is that polymers as a class of materials aren't only used in packaging. It's an important subsector, but they reach throughout our lives. And actually, I challenge you, Alex, to try and imagine a life without them. I think it's a distant memory rather than any kind of vision for the future. So I noticed as I got up this morning that, I put on my trainers with their polymer soles. I went to the swimming pool and put on my swimming costume made of polymer, came home and made my breakfast using all kinds of polymers, and got on my bike with its polymer tires and rode to work. And none of that involved a plastic bag, but every stage of that journey involved a very high performance material, absolutely optimized for its use. And so, in future, we definitely need these materials. And by the way, we need them in order to have the industries of the future that we want to reach net zero with. So, for example, we need them for batteries, for electric vehicles. We need them for a future which has automation and robots. We need them for medicines. We need them for electronics that don't have screens that shatter. And we need them for water purification. So there is absolutely no need to ban plastics or to envisage a future without them. But what we must do is deal with the very real problems that have been caused through a design flaw in the 1950s when the majority of these materials were conceived.
Well, let's get back to the fact that when I teed up this question, Jo very nicely was like, okay, here are my points. Your first one was like, Alex, I challenge you, like putting me on the spot. I don't have the expertise of a chemistry expert at the University of Oxford. Yeah. But what I do is I have a braggadocio nature. So yeah, challenge me. I have no distant memory of these things. I was born in the 90s. I don't remember a time before plastics. Okay. So you're basically saying, if I understand correctly, that it's not about plastics themselves. It's about how we use them, which I guess has been, I think, a takeaway from nearly every episode in this series. Since both of you are sort of looking in similar areas around this, I mean, could you tell me a bit more about your own research that's aiming to tackle the plastics problem?
My team here at the university work on two aspects of this problem. The first one is, what do you source the plastic from, and how do you efficiently manufacture it? Because we're talking about a really big scale production material. And so we need to have really cost effective, really efficient ways to make it. The second aspect of the problem that we work on are what's the properties of that product that we make, and how will it perform in use? And then what are we going to do with it at the end of its life? And because, as I've alluded to in the opening, we really focus on non-petrochemical raw materials, we have a really unique set of opportunities by doing that. And the first is that we're able from the beginning to design in points into our polymer, into our plastic, that allow us to more efficiently recycle it or allow us to biodegrade it at the end of its life. So we can kind of sort that from the beginning. And when we talk about design in chemistry, we mean design on a fraction of a millimeter scale, Alex. You know, it's really extraordinarily small, this design. But we're designing the molecules so that they give the performance that you want in terms of toughness or stress strain or adhesiveness or scratch resistance. All of those properties that we want, we're designing really from this very tiny length scale. And then we're also considering what happens at the end of its life so that we can make sure that when we've finished using it, we either reuse it or we recycle it, or after all of those options are exhausted, there is a viable way to break it efficiently into things that we can then upcycle or reuse, as Joe has said. And that means the chemical industry, that means the industries making these materials.
Okay, and so from the chemical industry to chemistry, but turned biology, which is my favorite thing. Joe, what's your work looking at?
Yes, as I said at the beginning, we're really quite focused at the moment on looking at end-of-life solutions for plastic that's already accumulated in the environment. And so we have focused so far on PET, which is a very popular thing to focus on. So that's the stuff that plastic bottles are made out of, polyethylene terephthalate. And what we are doing is developing microbial technologies which will take the monomers which we can get from PET. So we know already how to use enzymes to break down PET into its constituent monomers. And there's a lot of research around the world going into making these enzymes more efficient. But what we're interested in doing is taking the monomers that you get from these degradation processes and actually upcycling them on a molecular level into high-value small molecules. So just one example recently is that of upcycling terephthalic acid into vanillin, which is something we published earlier this year. And so this is an example of a really high-value molecule. It's used across the flavors and fragrances industries. And it's currently synthesized actually from petrochemicals on quite a vast scale. And so the fact that we've actually shown that we can convert plastic into this high-value material, I think really shows that you can start thinking about it as a resource and not just a waste product. And moving forwards, we're also interested in understanding how microbes interact with plastic degradation monomers. So we've heard from Charlotte, there's really exciting research going on designing new next generation polymers for degradation. But what I'm quite interested in is once we degrade these and say you put them into a landfill site or a compost heap, how are those degradation products then going to interact with the microbiome within that environment? And are there actually any enzymes which might be present within that microbiome, which we could be using for upcycling technologies? So there's a few arms to our research. So both rationally designing, if you like, new pathways, and also more of a sort of discovery project to try and find out more about what's going on already and then designing that into new technologies.
Joe, this is fascinating, the ability to make vanillin from terephthalic acid. I wonder if you could comment on the natural biosynthesis of vanillin and the extent to which you've had to tweak those processes.
Absolutely. So naturally, vanillin is made from a vanilla plant. I've actually got one behind me. That's a vanilla plant. It was a gift from the group.
This is an audio medium. No one can see that.
I know, but Charlotte can see it. So yeah, it's made by a member of the orchid family via ferulic acid route through a series of biosynthetic steps. And naturally, it's prepared. It's made on reasonably low yield. And you might have heard of natural vanillin. It's very expensive. It's from Madagascar and Ecuador, various sort of tropical countries around the world. It's extremely expensive, but that just cannot meet the demand. And so there have been many other routes, both biosynthetic and chemical, to make vanillin. The route that we've actually used is actually very different from the natural biosynthetic route because we're starting from a different building block, which is terephthalic acid, rather than the sort of amino acids, I guess, which the biosynthetic route would go from. So we have actually heterologously expressed various enzymes within our microbial cell from another organism, which specifically take terephthalic acid and will then convert it into vanillin. So it's a completely new biosynthetic route that we developed.
Okay, so that last part you're going to have to explain, because all I heard was heterologically, and then my brain went silent. So if you could explain, it's okay. English, I guess, is my first language, maybe second. I don't know. I've lost count at this point. What does that mean, heterologically expressed?
So heterologously expressed. It's always a difficult one to get out. So that basically means taking the genes from one organism, or a gene or a cluster of genes from organism A, and inserting them into your host organism, which in biotechnology is very commonly E. coli. We do use other things as well, but E. coli is a very popular starting place. So you take basically the genetic material, the coding material for those enzymes, you put them into your E. coli, and then you basically hijack the E. coli's protein-making machinery and tell it to make these genes or make these proteins that these genes are encoding that you've inserted in. So it's basically a process of expressing a non-native enzyme in your chosen cell.
So, okay, both of you, that's super interesting. Like, my brain is like, both of you are sort of looking at it in kind of small scales, like it's still at the research sort of phase here, but like practically, because we're looking at the future, or in Spanish, el futuro. So how might these innovations like work practically in the real world, like getting them out there? I mean, what do we need to do to make them sort of useful on a large scale? Joe, I'm going to start with you.
Yeah, this is a really big challenge. This is such a new field. I mean, this idea of plastic upcycling has really only taken off in the last 3-4 years. It's very, very young. And all the studies that have happened so far really have been on very small lab scales, and that including mine. So yeah, really the first challenge is breaking down the plastic on scale. This is something which has been begun to be commercialized. So there is a company doing this in France called Carbios, and they use enzymatic process to degrade PET, and then they recycle the monomers back into new PET. So they've demonstrated that it's scalable. And the question is now, can we integrate that scalable PET degradation with these upcycling bioprocesses? And before that can happen, we really need to improve the efficiency of these bioprocesses so that they are making much more of your target molecule within a shorter space of time under less forcing conditions. So for example, in our study, we had to use a lot of cells to get reasonable conversions. So we need to actually improve the efficiency of the chemistry going on in those cells so that we can use fewer and then have more favorable processing conditions so that it becomes scalable. And that's the challenge for the next few years, is to use the tools of synthetic biology and biocompatible chemistry, or chemistry if it's just a chemical process. And without the biology, we really need to intensify these so that they do become scalable. And then start demonstrating it on scale and showing that it can work.
Okay. So with that, and I'm going to be asking Charlotte this after I ask the first question, but like, what does a world look like in which your work is successfully scaled up?
Yeah, this is a very difficult question. I mean, the plastic, specifically the plastic waste problem, is so it's so sort of permeated throughout multiple layers of society. So first we need to address the kind of consumer side of it and try and convince the public that it is worth putting their plastic in the right box, and then there's a lot of work to do with councils and recycling facilities to start introducing these new end-of-life options rather than shredding, for example, shredding your PET and turning it into fibers or synthetic fibers for clothing, to actually demonstrate that there are other options for these recycled materials. So there's a huge piece of work to be done, and as I said, it spans sort of public engagement, councils, recycling centres, what have you, and then there's that sort of crossover then with processing plants to actually put some of these technologies into action and scale them up. And I'm not going to lie, I think that process will take many years to really become efficient and smooth, but as I said, we're at the beginning of a very long journey, I think, and we're just really opening our eyes now to the fact that we need to change something. So I'm optimistic that these things will happen, but I just think we do have to be maybe a bit patient with it and keep pushing, except that it will take years to get these processes and get these different parts of society talking to each other.
Look at that. We're going years and years ahead. I like it. It's on brand for this episode, the future. So Charlotte, I'm going to ask you the same sets of questions here. First and foremost, like in the real world, your work, yeah, like what needs to happen in order for it to be like useful on a super large scale, like everywhere? Let's say, I'm not going to say the entire world. Let's say all of the UK.
One of the areas that we work in is using carbon dioxide directly to make polymers from. And in this area, what's really important is to understand the manufacturing process and the catalysis that lets you activate carbon dioxide and turn it into a polymer backbone. And in order to do that, you have to have another chemical present. And that chemical can be a petrochemical, or it can be a naturally occurring biochemical, or it can be bioderived. And so what needs to happen in order to scale these technologies is a number of things. You have to have technological advances, and Jo referred to some of them in her field. In this field, it would be about the efficiency of the catalysis, the process and how efficiently that can operate, how scalable all of that is. And you also need to have a really excellent set of properties for those materials. And one of the advantages of putting carbon dioxide into the backbone of these types of materials is that you can improve some of the physical properties. For example, UV resistance. You can make films that are beautifully scratch resistant. You can make high performance synthetic rubbers. You can make foams. But you also have a really big environmental benefit, because you can save 3 times as much carbon dioxide as you would by making that material in a conventional way. So you save not only by directly using CO2, but you save twice more by not using the petrochemical. And so in this field, what we also need to do is to create the market pull and ensure that the customers that might want these types of products can be supplied them by the middleman, by the chemical industry that makes all of the raw materials for the stuff in our lives, right? For all the things we began with, the products around our home, the insulation foam, the mattresses, the shoes, and so on. And so that's really important too. And then a final aspect of ensuring that you design the chemistry from the outset for scale is to really work on this idea of precision at the molecular scale. And so in the past, when plastics were initially conceived, they were just produced in really efficient ways, but we didn't quite understand. We weren't able to fully appreciate the structures across the length scales, and particularly at that very tiny molecular scale. Of course, we're in a very different position now. And so what we need to do in order to scale these technologies is start at a tiny scale with really deep understanding and proper design, and make sure that the materials we're using are cost efficient, manufacturing methods are really optimized, and that the products we're delivering have the right properties. And I think if you can meet those needs, then there's every hope that you can change these industries and scale these products.
Okay, I love it. Both of you, I love the answers both of you given, because there's so much hope in your voice. Like when we've spoken to previous guests, they're sort of like, yeah, you know, and this could happen. Yeah, no, this could happen. Both of you are like, yeah, this is gonna happen. It's great. We're gonna like put pressure on people, and then things are gonna happen. I love it. Previous episodes, right? We've heard about recycling, composting, hot composting. That's a weird thing. These things are smelly. Reusable plastics, upcycling, downcycling, no left or right cycling, which I feel is a bit, I don't know, it's a waste. Bioplastics and so much more. With those things I've spoken about, the ones that are real, how do they all fit together into this idea of a sustainable future of plastics? Like what's most important? Because to me, the thing that jumps out there is like recycling and composting.
I think it actually involves a combination of all these things. So the plastics problem is very complicated. And as I said before, it spans so many different aspects of our lives. And I think in practice, what we're going to have to do is, have a toolbox of solutions, end-of-life solutions for different types of plastic and different situations. Some of these might be kind of in situ on the field type solutions, and some might be more centralized. Say, you put your particular type of plastic in a particular recycling box and it goes to a central process. And other things might be designed for end of life, so they might decompose. I do feel that we shouldn't, my personal opinion is that when it comes to composting, that should be a last resort solution. And that's because, even if you're working with a biodegradable plastic, this is still made of essentially carbon, right, and oxygen, which is still resources, and we can still use those as, in my field, you could use them as carbon and oxygen sources for microbial growth. And once you have microbial growth, we can program microbes to make all sorts of very useful products. So I think simply putting a plastic bottle on, or whatever plastic it is, on the compost heap and just letting that seep away into the environment, I personally think is slightly wasteful and not a truly sustainable solution. And as I said before, we actually don't know the effect that will have on the local microbiome within that environment. So my personal opinion is that we should try and have composting as a sort of last resort, and have sort of upcycling and recycling technologies as what we're aiming for and what we're designing for.
Okay, so now I'm being told by experts that plastics, in my head, and I'm sure in the head of lots of people who are listening, composting and bioplastics and all of these things sound like, oh yeah, this is really good and sustainable, like a good thing we should aim to. But now you're sort of saying it's more complicated than that. Charlotte, what are your thoughts? Please make it even more complicated than that. Blow my little brain away.
In the past, in the chemistry world, we've tended to think about polymers as a chemical structure and then group them accordingly. So we think of polythene as the set of carbon-carbon bonds it contains. And perhaps if we're thinking in a little bit more precision, we might think about the set of properties mechanically that it delivers. In future, I think we need to have a different taxonomy in a way for plastics, and we need to think about their chemistry according to the timescale that we need them for. And so there will be a set of materials that are very durable, and we need them to perform as such. For example, water pipes or construction materials, or the materials that your car is made of. This doesn't mean to say that we completely ignore what happens to them at the end of life. They're still designed to be recyclable, as Joe says, at the end of their life. They're still designed, after recycling becomes unfeasible, to be broken and used then either in the ways that Joe describes, by upcycling, or put back into manufacturing. So there's a whole set of materials that are durable, and we need to treat them as such. There's another set of materials that are the obvious plastics that are disposable. And in that scenario, I agree with Joe that recycling is very important, and including the recyclings that involve reuse, that don't involve any energy input. And we should have a hierarchy where we drop down only to going back to raw material if we absolutely have to.
So, I mean, don't feel bad, both of you, because every single guest that we've had on has given an equal amount of caveat and complication, if not more. You've actually made it the most simple out of everyone. So thank you. That's why you've got me smiling. I feel as though like the best way of getting this plastics problem sorted is by taking all the guests that we've had and then just like melding them into one person with, you know, all of this biotech knowledge, this manufacturing knowledge, economics, composting, everything, and things will get done. But unfortunately, I don't have that power just yet. And other scientists, I assume, don't have that power. In order to solve some of these problems, outside of the sphere of research, what's needed to make things better?
A lot of change, I think. So we need, so I think it's got to start with people actually believing that there is a problem, and it's worth investing both time and resources and money on putting infrastructure and policies and workflows in place to address this problem. I think this process is now underway, and people have begun to, there is already a sort of mind shift and a change in attitude towards plastics, and there's now recognition that there is a problem that needs addressing. I think a large part of this will be sort of a policy piece around, sort of certain incentives perhaps to to incentivize the process to make this more attractive, both to consumers but also to large companies. So they have a responsibility in, I think, designing their products to minimize packaging, for example, and the packaging that they do use, to think about where it fits into that framework that Charlotte's just outlined, and how it's going to fit into that and what its end of life process will look like. I don't think we can purely just rely on the consumer to sort of do the right thing with their plastic. I think that's perhaps too big an ask from the consumer, and it's difficult, you know, when you've got this sort of complicated piece of packaging and you don't know what to do with it. So I think there is a lot of responsibility on the manufacturers of the products in the first place. And then there's a huge technological piece that needs to go alongside this. So it's all very well everybody wanting to do the right thing and there being policies in place, but we actually need the science and the technology that can deliver these solutions as well. So I think these things will run in parallel and then hopefully converge in the future to give us a more sustainable future.
Absolutely. Everything Jo says is very sensible. And what we need to do, to return to where we opened with, is ensure that this joining of the two cycles of the carbon cycle and CO2 emission cycle and plastics production are linked legislatively. So certainly we need much more legislation to control carbon dioxide emissions and mandate that this is part of the consideration and the penalty that you pay when you produce plastics if it's not factored in correctly so that they're net zero. That is essential, and that must happen quickly. We don't have time to muck around here. So I'm not smiling anymore, Alex, because we know that we're facing a climate emergency if this doesn't happen. And this industry has to decarbonize, and it has to do it super fast. Now, the good news is that that's not too hard to do, because, you know, the redesign of these materials really is a technically solvable problem. But as Jo says, in order to change the way you do things, you have to overcome the inertia and things will be all right, we just keep doing things the same way we've always done. We can't do that. We have to change this sector. We do have to make some investment. Now, some of that investment will pay off because we can get a synergic gain by coupling these new products, these much more carbon efficient products, with growth sectors. So as I alluded to at the beginning, we're going to have a mass electrification. We're already having that in transportation. We can couple that with making sure that the materials provided to house batteries, even some of the electrolytes in batteries, are the right polymer materials and the ones that have these correct life cycles. We can do the same with growth sectors around automation, robotics. We can do the same in healthcare. We can do the same in packaging. The other thing I think that is important is not to burden shift too much onto the consumer here, because they really don't have a lot of choice in what they buy. And I think the consumer has a really in the main is trying to do the right thing in a very complicated and not very well set up system. And so what's really important is to not lose sight of the fact that the majority of the production of these materials happens by about 10 to 20 companies in the world. And they need to be regulated to do the right thing and not produce materials that are going to cause a massive environmental burden for us and a very unfavorable carbon dioxide balance. And so for me, really, it is important also that we have an agenda to begin to phase out the use of certain materials that cannot be properly recycled, materials that cannot be biodegraded. They should not be used in certain sectors. So although we began very happily and very optimistically, there are things that are tough that must happen in this sector.
So, I mean, Jo, are you enjoying the fact that Charlotte started off with like, oh no, we can't get rid of plastics? Like both of you are like, you can't get rid of plastics. That would be bad. And now she's on the, okay, we can't get rid of plastics, but some people should not have access to plastics. Certain people should not have access to certain materials.
Some plastics should be banned, in my opinion.
Yes. Okay, we're there. Which plastics should be banned?
That's going a little too far, but I gave you the criteria for how you should make that decision. You should seek to phase out materials that cannot be recycled. You should seek to phase out materials that are irretrievably distributed in the environment and are not biodegradable.
Okay. We got two. I like that. All right. What information do you feel, based on like your work and looking at this field more generally, What information do you feel that like policymakers need to have from scientists or other experts in order for them to make the best decisions?
I think they need to know the state of the art now, and they need to understand the direction in which these fields are heading. So both from the design point of view and from the sort of degradation upcycling point of view, almost so that, I mean, and obviously this isn't totally predictable because, you know, science is inherently unpredictable. We can't completely say that some things will be possible, but we have a general idea, I think, of directions in which these fields are heading. So I think, you know, policymakers need to have an appreciation of this such that they can align their policies over the next 5-10 year period to fit with the technology that is expected to be emerging within that time period. That's much more efficient than getting, you know, to somewhere 10 years ahead and saying, oh, we've got all this stuff. Okay, now let's spend 5 years figuring out how it's going to be used. Let's actually design the science and the policies together, you know, with cross discussion ongoing, so that we can implement those as soon as the technology is ready.
When I began my career, I was also working in renewable energy. And at that point, I don't really wish to say how long ago, but a couple of decades ago, people would say, yes, well, you know, we might have a bit of renewables on the grid in the UK, but the real answer is going to be this, that, or the other. And it seemed also intractable, and it also seemed decades of deployment. And yet now we're living in a UK in which renewables can well exceed non-renewables on the grid on a regular basis. We're living in a world where net zero electrified transportation is really rapidly becoming a reality. And so you do need those, you need to consider that things can very suddenly change, and they must in this area, and they must. We have the same thing if you look at the problem with the ozone layer, and, you know, the world was able to come together through treaties to really significantly reduce the use of CFCs and to remediate that environmental problem. And so I think that the plastic sector has all of those factors aligning. It has a really big environmental problem. We have an absolutely pressing and urgent need to decarbonize. And there are a range of solutions, some of which are closer to being ready than others, but there are a range of solutions that are fit to go to market.
Charlotte, I'm going to start with you because you had a lot to say, and it gives Joe some more time to think about this. So, Charlotte, what would your key takeaway be for our listeners? What would you want them to know?
I would want them to know that the problem of the plastics we have today is solvable. And furthermore, we can have a much better future in which we have all the things that we want and need, all the properties that those plastics deliver us, but without all of the problems that exist today. And I would want them to know that this is an industry that can and must decarbonize.
Joe, what about you? What's your key takeaway?
I'm going to stick with the optimistic tone. I would like to really get across the message that I see this position that we are now in as an opportunity. And this is a real exciting opportunity for change, for rapid change, which does need to happen. And we should start viewing plastics as a resource. We shouldn't just see them as a problem and a waste product. We should start thinking about these holistically and, you know, as I said, as a resource.
Well, thank you so much. This has been fantastic. You've given me a lot to think about. And so, yeah, thank you so much.
Thank you, Alex. Nice to meet you.
Thank you. Bye. And now it's time to hear some news brought to you by our reporters from the Royal Society of Chemistry.
Hi, I'm Lizzy from the Royal Society of Chemistry, and today I'm chatting to Rob Nicoll, who's the co-founder and chief marketing officer of Chip's Board. So, Rob, can we go straight in and you can just tell us a little bit about what is Chip's Board and what do you do?
Absolutely. First, thanks for having me. It's great to be here. So what is Chip's Board? The elevator pitch is Chip's Board is a company that turns industrial food waste into plastics. That's the very quick description. Essentially what we do is we take all of the waste, all of the food items that these industrial food manufacturers have left over. So it's important to state that we're not taking food out of anyone's mouths or diverting a a valuable food chain, but we're using everything that these companies are considering currently as a waste. We're taking them and we're valorizing that waste through various processes to create a plastic pellet, which can be 3D printed, injection molded, all sorts of things. So hopefully wonderful, incredible products and inventions can be made from our materials moving forward.
So how did you come up with the idea to do this, or how did you get involved in this?
So the company was founded by myself and my co-founder Rob Nicoll in 2017. So that was our third year of university. It's important to mention, especially on a chemistry podcast, that myself and Rowan didn't do a chemistry degree. We have sort of GCSE and A-level chemistry moving into starting the company, but we were studying design. So we were both designers. We were both making a lot of things. So new products, installations, all sorts of things that surround sort of physical design. And really, it was the shock realization about the amount of material that we were using as designers in our own practices. So using huge sheets of MDF, sheets of plastic, foams, all of these things that really, one, as a student project, you normally make these things or build these things for maybe 3-4 weeks, and then you have to go in the bin because there's nowhere to store them, and you've got the mark, so that's a tick, and then you can just get rid of the item. So really sort of unsustainable practices around quick turnarounds in design and building. But the industry as a whole, looking at installation design, you've got window displays, all of these things have a finite use of time. So like maybe seasonal, maybe weeks, months, maybe years. But fundamentally, a lot of these custom-made objects are built to last a very small period of time.
Cool. And so how did you then take from those concerns, I guess? How did you go from there to actually starting this company? And how do you actually go about what do you do? So you've got food waste, you're turning to plastics. How do you do that? Where do you get it from? What happens?
So yeah, so the first product we made actually wasn't plastics. It was an alternative to MDF and chipboard. So essentially we were getting this waste, we were compressing it and smashing it and heating it and doing all these different processes to create a panel. This sort of the idea of using food waste to create these viable materials gained us a lot of traction with some awards. So we were the Santander University Entrepreneur of the Year 2018. We're finalists in the Mayor of London Award and the Royal Academy of Engineering Launchpad Awards. So we're very successful in a lot of awards through the materials we're making at an early stage. This success came with funding, a lot of these awards, which allowed us to bring on board an incredible team of chemists. So we have polymer chemists, biochemists, biotechnologists, all sorts of incredible people with accolades much broader than I can fit into the time we're chatting now. But what this did is it allowed us to really sort of sidestep and review the materials we're making and realize the potential. So it's all about potential. We look at waste and you look at potential that waste could become. We weren't actually fulfilling the full potential that waste had. So we were able to sidestep and look at using the elements within this waste. So looking briefly stepping into how the product works. Once you have a waste product, you're able to obviously break it down. You have to modify, you have to unlock the potential that these waste streams have to create building blocks to create something much larger, much more exciting. To put sort of a very complex chemistry process in a very simple terms, I often describe it as Lego. You have all your different size pieces, shapes of pieces, but that gives you the ability to create something much larger and much more impressive. So yeah, just sort of it stemmed from an idea, a concept that me and Rowan were able to visualize, and then just the support of the entrepreneur community, the innovation community, and the science communities, both through funding and other supports, allowed us to grow the team and really grow into the material that we're producing today.
So what products do you make now from the food waste?
A question we get all the time is what products we make. So we are the material producer. So we don't necessarily make end products that the consumers would buy. One thing that's important to say is we are also looking at products from our end in the sense of material forms. So we would like to produce a pellet as a standard, which is sort of industry standard when you're talking about polymers and plastics. But we'd also look at from our facilities having filaments available for 3D printing, sheets, extruded rods, basically a lot of forms that artists, designers, and companies can use as raw forms. So as much as they are products that we would produce. But we've had huge industry interest from lots of different industries. So fashion is a really sort of dedicated industry right now to finding sustainable solutions. Not to make it seem all singing or dancing that fashion is the sustainable sort of revolution, but the reason that they're so passionate about it now is because they've done so much wrong for so long, and they're sort of coined as one of the most polluting industries globally. So that's where the real push for change is currently. So we're working with brands very large and small, and really having these conversations now to integrate our materials into their products. So a few of the brands are under close-knit NDAs, but I can say that we're working with brands like Ace and Tate, who make eyewear. So looking at how we can produce sustainable eyewear, which fits in really well with the lifespan of our product. So our materials are not intended, although they're sort of biodegradable and sustainable products, they're not intended used for packaging and coffee lids, so that you often see biodegradable materials used within currently. They are made to be used within products that have a slightly longer time frame, but because they are a sustainable material and they can be degraded or disposed of, they fit really well within products that last sort of, say, 5 to 10 years. And that fits in really well with timeframes and trends and sort of fashions and all sorts of things like that. So on average, a person would replace their glasses every 5 years. So that fits in really well with the life that we would like our materials to have.
Are you finding that there's a lot of appetite at the moment for materials that are sustainable or seen as sustainable because of kind of increased concern about the environment?
Oh, absolutely. A lot of people approach me in terms of, so I'm the marketing director. So a lot of people say, how do I get the word out there? And really the biggest challenge right now is how do I almost dampen the word slightly, because the amount of demand we're getting. So every industry, I've mentioned fashion, but every industry that uses plastic, and believe me, that's most industries, everyone is looking for sustainable alternatives. So I get emails flying into my inbox like every 10 minutes, like with new sample requests, wanting to talk about the material. Not everything is going to work. A lot of people may get in touch and say looking for a rubber alternative. Well, we can't really yet be a rubber alternative because you still have the restrictions of what the plastic can do. But there's a lot of exciting opportunities that we are talking about, and hopefully soon we'll integrate our materials within. An example I always give is, so the listeners won't be able to see us, but both of us have headphones on right now. Consumer electronics is such an interesting topic when you're talking about plastics, because the electronic components within these items, so I've got Bluetooth wireless headphones on, the batteries are only, say, certified for 5 years. The electronic components, the speakers, these components have a finite life. But the plastic casing on these headphones can last 2,000 years. So really there's absolutely no synergy between the components of the product, which makes it for quite an upsetting story, really. Actually, it's like parts of these components will be dead thousands of years before the rest of it even starts to disappear.
So can I ask a big question then, which is what happens to your materials at the end of their life? Are they any more recyclable than other types of plastics?
So that is the big question, and that is the big question mark around biomaterials currently. Our materials are thermoplastic, first and foremost, so it can be thermally recycled. So we can, obviously, you're going to see degradation the more times you thermally recycle a product. But we have equations and all sorts of things about how we can introduce new material with recycled material to make sure that our plastic remains quality throughout. It is biodegradable. Now, biodegradability, again, huge question mark, and around that, a lot of people are misinformed about biodegradability because they think of the apple core on the street disappearing within a couple of months or weeks even. But biodegradability essentially means that without any time frame, something will eventually return to the soil without having negative effects. So it could take 2,000 years, but as long as it completely disappears without introducing any microplastics or any negative effects, then it's biodegradable. So yes, ours is biodegradable, but I don't often like bragging about that because there's lots of things that are. An oak tree that falls down in the woods that will be there for hundreds of years is biodegradable. Doesn't mean it's going to go anywhere anytime soon. And then it's industrially compostable as well. And that's the biggest thing. So it's not home compostable because I often say that what good would a pair of glasses be that if you went out on a slightly humid day, they start to fall apart on your face? Probably not ideal for a product. So it's industrial compostable. And that's similar to a lot of this vegware that we see, a lot of coffee cups, these straws that people think are home compostable, but they do require a certain parameters, criteria for these to break down. And there is a huge pressure at the moment on sort of governments to introduce more infrastructure to allow ease of use for people to make sure that these products they're purchasing, be it packaging, be it other bioplastics, that there is the right way to enter those streams. Because most people will buy a coffee with a biodegradable lid, but they'll put it in the bin because there isn't a bin for biodegradable plastics or industrial compostable. So there's a lot of infrastructure change needed to make sure that we can make sure that the materials go into the right disposal or recycling streams that they need to go to.
That's brilliant, because that's exactly what most of our podcast guests have said, pretty much the exact same thing, is that it's all very well making all these innovations, but if there isn't the infrastructure, then it's not going to end up in the right place. And so I suppose the other advantage of your materials is at the beginning of life, right? So the process of making them, they're not coming from fossil fuels. Are there any other advantages at that stage, environmentally speaking?
Yeah, so essentially we are pretty much carbon neutral going into our process, because all of the associated carbon has been used for the main product, which is the food itself. So we don't take on any of the farming or the land use, because all of that is already sort of allocated to the primary use of the material that we produce. Obviously, transport is a small thing in terms of getting it to our facilities. But there's no associated sort of carbon or anything around the actual growing of our feedstocks, which is a big thing, because a lot of these traditional sort of vegware and these bioplastics, they grow vast quantities of corn or sugarcane to create these bioplastics. So you're still using virgin resources to develop a sustainable plastic. 10, 20 years ago, when these plastics started to really be prevalent in what we produce and sort of in the world of product design, they were the saving grace. They were the obvious next evolution in plastics. But now we can start seeing, what we can step off that again, and instead of growing virgin crops to produce these plastics, we can optimize a waste stream to produce these plastics. So it's all about constant evolution. It's not about necessarily blaming the person before us about what they've done wrong. It's about looking at what they've done, appreciating that was the next step, and then moving forward even still. So that's the large thing. We don't use land usage, we don't use water usage, we don't have huge crop yields that we have to maintain to produce our material. It is from a waste, which inherently cuts a lot of carbon and energy and all these things that other plastic producers do.
Cool, thank you.
No worries, thanks for having me.
Alright, so it's over now. We've truly come to the end of the series. I mean, thank you for sticking around to learn more about plastics. So it's been an interesting ride, right? Now, I don't know about you, but even though I'm not necessarily 100% pro-plastic, I've been joined by some fantastic guests who show me that it's not necessarily so black and white, and plastics might have a place in the future. Will this be the only series of Brought to You by Chemistry? Who knows? But if you haven't already, be sure to subscribe to this podcast to be the first to find out. As always, if you want to learn a bit more about the RSC and plastics, you can visit rsc.li/plastics. It was produced by Hiran Joshi and Elizabeth Ratcliffe and presented by me, Dr. Alex Lathbridge. See you next time.